I wanted to redo this problem because in the other video I had written g of x with an addition sign instead of a subtraction sign. So this is the corrected problem. We are asked to find the power series representation for g of x centered at 0 by differentiating or integrating the power series for f of x. So the first thing you need to do is take notice. Let me get a different ink here. Notice that g of x is a multiple of the derivative for f of x. So you really want to examine f of x and see if you can get to g of x by taking the derivative or by integrating. Okay, but you got to go this way. You got to go from f of x to g of x, either by differentiating or integrating. So notice that f of x or that g of x rather is a multiple of the second derivative. So g of x is a multiple of the second derivative. So let's look at that. F of x is equal to, I'm going to rewrite it in terms of negative exponent. Right, that's f of x. So let's take the first derivative of x. And the first derivative is minus 1 minus x to the negative 2 using the chain rule. That's the stuff, the derivative of the stuff. So this becomes 1 minus x to the negative 2. The second derivative is negative 2, 1 minus x to the negative third power. Again, applying the chain rule, we end up with 2 times 1 minus x to the negative third power, which is simply 2 over 1 minus x cubed. So we've got a multiple of g of x. So let me summarize that for you. So f double prime of x is equal to 2 times g of x. Or another way of writing that is just solve for g of x. G of x is the second derivative of f divided by 2. So we're going to use that relationship in order to come up with the power series representation. The second thing here that we want to examine is manipulating the power series directly. So knowing that g of x is equal to 1/2 of the second derivative, we can manipulate the geometric series. So f of x is 1 over 1 minus x, and we know the series representation for the geometric. It's k equals 0 to infinity of x to the k, right? And that's convergent for x between negative 1 and 1. So let's take the first derivative, manipulating the indices. So grab another color. When you take a derivative, that becomes a constant multiplier, right? And then you subtract 1. So this derivative, the first one, and I'll fill in the indices in a minute, is k x to the k minus 1. Now I'm going to start it at 1 because I took the first derivative. Okay, so I subtracted off an index here. Since I subtracted off 1 here, I'm going to add 1 here. Continue down here and let's find the second derivative. So the second derivative, manipulating the power series directly, grab another color again, is going to be k times k minus 1 times x to the k minus 2. And again, since I have subtracted off 2 for the second derivative, I'm going to start it off at 2. So f double prime, or the second derivative in terms of a power series, is written as such. So g of x is equal to 1/2 times the second derivative, which would be 1/2. And now I'm going to drop in the representation that I have, which is k equals 2 to infinity, k minus 1, x to the k minus 2. Now, I'm going to rewrite that in the form of the geometric series so that I can apply the convergence that we know for a geometric. And all I need to do here is I want to get this to be a k, right? So I'm going to subtract off 2 from the bottom, the indice, right? And I'm going to add 2 to everywhere where there's a k. So this becomes, right, k minus 1 plus 2, right? Minus 1 plus 2 becomes k plus 1. And here, this becomes k plus 2. So we've got, I'm going to order them a little differently, k plus 1 times k plus 2 times x to the k. And that's a geometric series. And we know that this also converges. For negative 1 to 1. So that's how you differentiate one function to get to another function through the power series.